Back, everyone. We're in chapter 12 on solutions, and this is the swimming pool section, 12.3 on solubility. We want to know that specifically in water, since we use water so much, and water is such an important part of this world, whether or not a compound will dissolve in water. And whether it will dissolve in water has a lot to do with how well the energy that it's put together with, and whether or not that it is ionic or other situations. But we're going to learn a whole series of rules and pictures to help us to learn what is and how to predict whether something will be dissolvable, which is soluble in water. So dissolvability is solubility. It's the same. It's the word. There's no such word as dissolvability, but solubility means dissolvability. So let's review our solubility rules swimming pool that my friend came up with. If you remember, anything in the pool is soluble. Anything out of the pool is insoluble. We have some things that are in the pool that have exceptions. So these guys over here has these exceptions. This girl here have these exceptions. And then you have some things that are out of the pool. I added a couple things that are not in this picture that I'll review with you. That will help you when you get to the solubility rules section of this slideshow. Okay, if you remember that in the pool we have alkali metals, which is group 1A, which is the lithium, sodium, potassium group. Anything that starts lithium or potassium or sodium, these are soluble in water. Okay, the next one I see here is nitrate. NO3 is nitrate. Anything nitrate, something nitrate is going to be soluble in water. Acetate, I think here is the picture of this crabby lady. I don't know why it was called acetate, but in any case, she is the representative of C2H3O2, which is -1, and acetate is always soluble. I added something here. I added a wet diaper, and a wet diaper is ammonium. Reminds me of ammonium. So NH4, +1, is always soluble in water. These guys over here, 7A, are anything in group 7. I believe that fluorine is insoluble, but chlorine, bromine, iodine are soluble. These are the exceptions to the solubility. This is a bullet, so that's lead. Lead chlorate, or lead chloride, or lead iodide is insoluble. Silver chloride is insoluble. In fact, it'll stain anything it touches. Don't get it on your clothes. Mercury bromide or chloride or iodide is insoluble. So these are outside the pool. This lady here is yellow, and I think this reminded my friend of sulfur. And sulfates, SO4, -2, are soluble with these exceptions. First guy here has milk. So that's calcium sulfate. Calcium sulfate's insoluble. Silver sulfate is insoluble. That's a coin, I believe. Thermometer here, mercury sulfate is insoluble. My favorite here is the tombstone, barium. Barium sulfate is insoluble. The barbells are strontium, like she's strong. So strontium sulfate is insoluble. And the bullet here is lead sulfate, insoluble. Over here on the side, hydroxide. I think her representative here is he's high and dry, because the sun has made him dry, and he's on pegs here, so he's high and dry. That's hydroxide, and it's all hydroxides are insoluble. I added another insoluble over here. Sulfides normally are insoluble, and at the top, oxalate, which we didn't learn on our list of polyatomic ions. I believe it's CO4 -2. Oxalate is insoluble. Carbonate, CO3 -2, is insoluble. That's fuzzy bear, so phosphate, PO4 -3 is insoluble. Okay, that should help you a lot in this section, I believe. So solubility is the maximum amount of solute that dissolves in a specific amount of solvent. Okay, so normally it's expressed in 100 grams of water. So how much water does a certain amount of stuff, how many grams of it can dissolve in 100 grams of water? Okay, so we compare apples to apples and say, here's 100 grams of water. How many grams of this dissolves in it? Or how many grams of this dissolves in it? Is it 0? Is it 100? Is it 1,000? All those will then be compared in how soluble something is. And we already talked about that the water could be saturated. Eventually that 100 grams of water is completely used up and anything else would simply fall to the bottom of the test tube. Unsaturated solutions contain less than the maximum amount of solute. So if you still have water in this case, or any type of solvent in this case that, or generally that has the ability to hold on to the solute, then it's unsaturated. It's still got plenty of room for those to solvate the water. There's plenty of water to wrap around new solvate, so it would be unsaturated. Saturated, on the other hand, is completely full. Every water molecule there in that jar is holding on to some solute already, so if you add more solute, nothing happens. It simply falls to the bottom. Nothing more can be dissolved. It's completely saturated. Okay, so what happens here, this is important, and I've not mentioned it before, so if you look at it, the solid dissolves and the solution crystallizes back into solution. So what happens is that even though it looks like that nothing else happens, you pour more salt, say, in that water, and it just piles up on the bottom, it's actually dissolving. The stuff on the bottom is dissolving into ions, but at the very same rate that it's dissolving, the solution is falling out of solution. The ions that have dissociated come back together and form a crystal and then fall out. So it's not that it's holding on to the ones that it already had. It's holding on to the same amount, but that the molecules are all different. Okay, that's those salt formula units are all different salt formula units that's holding on to, but it always has the same amount. And I'll try to explain that in class if that's still confusing. I'm sure it is. So comparing unsaturated and saturated simply means you can keep adding. If it's unsaturated, you can keep adding solute and it'll dissolve more. If it's saturated, it won't, and you end up with stuff on the bottom. There's tricks. I think I mentioned in class that you can, like if you want iced tea that's really sweet, you can order hot tea, put your sugar in your hot tea, and the high temperature helps it dissolve. We're going to see that the temperature affects solubility, and then more of it dissolves, and then if you slowly cool it down, you can get what's called a supersaturated solution, and we'll play with that later. That's really fun in the lab. All right, so let's look at temperature. You've got these J curves here on this graph, which means as the temperature increases, the solubility increases a lot. So every degree of temperature it goes up, the solubility rate goes higher, higher, higher. So it's not just higher as it's, more soluble as it's higher temperature, but it's very much more soluble every little bit of temperature that you increase. So most solids increase as temperature increases. What you're going to find is that's the opposite for gases. Think about fishing. If you want to fish for trout, you do not want to fish in warm water because warm water does not hold on to oxygen, and fish will always be where there's lots of oxygen. So fish want cold streams where that water is turbulent, so that air is actually mixing in with the stream water, and that oxygen is in the water so the fish can breathe well. In a still warm pond, say like a backyard koi pond, if you don't have some trickling water that's going to put some oxygen in it, all of your fish will die. Okay, I've killed plenty of that way. Henry's law. Here's another guy who has a law. Everybody has a law. He basically says that the solubility of a gas is not just dependent upon the water, meaning that solubility drops as the temperature goes up, but also in the pressure. So Henry's law deals with solubility and pressure. And this is not hard because all you have to think of is a bottle of pop. If you have carbonated soda, which is just soda water, which is carbon dioxide gas dissolved into water, lots of it will dissolve as long as you're under high pressure. The more pressure you have, the more the gas dissolves in the liquid. So what they do is they put carbon dioxide gas under high pressure. It dissolves in the water. The water already has some sugar and some flavorings in it. That's really yucky if you've ever had flat pop. Then when you open the bottle or you open the can, what you've done is you've released that pressure, and all the bubbles of carbon dioxide gas that are dissolved in the water immediately come out, and you get fizz. And that's the fizz of pop. And so Henry's law says the more pressure, the higher the solubility. It dissolves more and more carbon dioxide the more pressure that it's under. That's a pretty cool law. I wish I had that law. Soluble and insoluble salts. This is one of the coolest of the labs that we're going to do this year in terms of just dropping stuff in and seeing if it's insoluble. If it's insoluble, it forms a solid, and the solid precipitates or falls out of the solution and falls to the bottom of the test tube. If it's soluble, nothing happens. It's very boring. All the soluble stuff is boring as it can be because you have one colorless liquid, you pour it in another colorless liquid, and nothing happens. Okay? Actually, lots of stuff are happening, except that they're both soluble, which means they both instantly dissolve again, and it doesn't look like anything happens. If something is insoluble, that's when you get something pretty. So you drop something in, and it turns yellow or red or green or whatever. Those are insoluble salts. So if it doesn't dissolve, it's insoluble. If it does dissolve, it is soluble. So here we come into the solubility rules. Now, if you remember the swimming pool, this is just free, okay? Otherwise, you're going to have to memorize these rules, and I think they're hard. So basically, soluble is going to contain typically one ion from groups 1A. So anything that's 1A is going to be soluble. If you remember the swimming pool, the alkali metals, which is group 1A, are always soluble. So if it's soluble, they'll either contain that nitrates. Okay, if you remember the guy with the heart attack, the nitrates are soluble, acetates are soluble. Okay, normally any other combinations are insoluble. Now we'll see that there are some exceptions. Remember, the yellow lady, the sulfate, is soluble under certain conditions, but insoluble in others. The group 7 is insoluble, or soluble in some conditions, insoluble in others, and ammonium's also. Unless it's combined with like Fozzie Bear and stuff like that. We'll look at all the exceptions in class. Okay. So the solubility rules predict whether it's soluble in water. That's the obvious thing. And if it's not soluble, it'll form salts or solids that fall out and precipitate out of solution. Okay. So here's some examples. This is soluble. So what is it? It's potassium sulfide. Now remember, sulfide usually is insoluble, but it's bound with a group 1. And group 1 is always soluble, so this is soluble. Calcium nitrate, nitrates are soluble. Lead chlorides, okay? Chloride is usually soluble. It's in the pool, but remember there are 3 exceptions: silver, mercury, and lead. Lead's 1, so it's insoluble. Sodium hydroxide. Sodium hydroxides themselves are usually insoluble. They're high and dry. But if it's group 1 hydroxide, then anything that's group 1 is soluble. And here's aluminum phosphate. Fozzie Bear is usually insoluble. Okay? So that's just how you use the solubility rules. Okay, so equations for forming solids. What you're going to see in these, and these are awesome. I love this, and this is just so chemistry looking stuff. Okay? You've got compounds. And when you have aqueous, now we've seen aqueous before. It's not solid, it's not liquid, it's not gas, it's aqueous. It's dissolved in water. If you have something that's ionic, say lead, which is in this case +2, and nitrate that's -1, these are charges. These are ionic charges. If you have ionic charges inside water, they're going to form ions. They're going to dissociate into lead and nitrate. In this case, sodium chloride, these are charges. They're going to separate into sodium and chloride. So what's going to happen is they all break up and they all swim around together. And then they're bumping into each other and then coming right back again. The only thing that will happen is if they bump into something that doesn't break apart again, that's called a solid, and it falls out of solution. So the leads and the nitrates break apart. If they ever bump into each other again, they'll just break apart again. They're just easy to break apart because the water pulls them apart. The sodium chloride break apart. If they bump it in again, they break apart again. But what happens is that the lead and the chloride, remember chlorides is group 7, it's usually soluble, except for lead. Lead is one of the exceptions. So if lead and chloride bump together, they will form a solid and they will not break apart again. They will keep being a solid. They're no longer soluble in water and they fall out of solution. The sodium nitrate here would just break apart again. So what you have is you have two colorless liquids that you pour together, and what's going to happen is you're going to get the lead chloride as a product. Okay, and this takes a little bit of thinking because this to get your head around, but you're looking for insolubles. If everything's soluble, essentially nothing's connected. Everything's floating separately. If it's insoluble, then it connects and falls out of solution. Okay, so a chemical equation shows you all of the compounds that you're getting. An ionic solution equation breaks everything down into the ion. So look, here lead nitrate will show up as lead 2 and 2 nitrates. See, there's two of these, 2 NO3s, so it's going to show us 2 NO3s. These guys are going to break up because aqueous breaks up sodium chloride, and there's 2 of each, so there's going to be 2 sodiums, +1, 2 chlorines, -1. Here's the yield sign. Lead chloride is insoluble, so it doesn't break apart. It stays as lead chloride. Sodium nitrate is soluble, so it breaks apart into sodium and nitrate, and there's 2 each, so it breaks into 2. So anything that's showing the ions is called an ionic equation, and then the last one's called a net ion equation. If you have the same things floating on both sides, you ignore it. So let's look. I've got nitrate over here, it's aqueous, floating around. I've got nitrate over here, floating around. They're not doing anything. It's not making anything, so I'm just ignoring that. The lead, I've got lead on this side, but I don't have lead by itself on this side. I have it part of this product, so it stays. So I want the lead. I don't want the nitrate. How about the sodium? If I see sodium, there it is. It's on the other side, exactly the same, so I'm going to ignore it. These are called spectator ions. They are watching. They don't do anything. They just hang around. So that you get rid of all the hangers on, and everything that's left you leave in your final equation, which is called net ionic equation. So you've got lead plus chlorides yields lead chlorides, and that is all that you're actually making in this. So when you put lead nitrate with sodium chloride, what are you making? You're making lead chloride. Well, what are the ingredients of lead chloride? Lead and chloride. Everything else that you poured in the test tube doesn't do anything. It just stays in the water. It stays in the water, and then you throw it away at the end. Okay. Here's some examples. Here's silver nitrate, or silver chloride. So silver chloride is insoluble. It's one of your 3 exceptions for group 7, and so it forms a white blobby precipitate and falls to the bottom. Okay. So if you are writing equations with an insoluble salt, this is an example. So write the net ionic equation for a reaction of barium nitrate with sodium carbonate. Okay. Well, carbonates, if you remember the coal, it's usually insoluble, but sodium is a group 1 and it's always soluble. So this is soluble in aqueous, in water. Barium nitrates are all soluble. So all of these are soluble. So you have these are colorless liquid, this is a colorless liquid, you put them together. So you need to know what are the ions. So you break everything apart. Well, nitrate's -1, and there's 2 of these -1, so this must be +2. That's how you figure it out. So this is Ba +2. It's also in groups 2, so that'll tell you that it's +2, because anything in group 2 is +2. I've got 2 nitrates, because there are 2 of these, 2 nitrates, and so nitrate's -1, so I have 2 -1s. I've got sodiums, these are aqueous, so I've got it's Na2, so I have 2 sodium positives, and I have 1 CO3. That's a carbonate, and they're all floating in the water. That's an ionic equation. Okay. Now, which one of these If they bump into each other, will form a solid. Now, if barium and nitrate bump into again, they'll just re-break apart. Okay? They're like a high school romance. They never stay together. They just break apart over and over and over again a million times. Okay? Likewise, sodium and carbonate will always break apart because they're always aqueous in water. What are the other options? Let's take these positives and join with the other negatives. So if I have barium nitrates, all nitrates are, if barium and nitrate join together, nitrates are always soluble. So they're just going to break apart again. What if I had sodium? What if I had barium and carbonates? Well, all carbonates are insoluble except for group 1s plus ammonium plus, nope, that's it. They are insoluble. So what you're going to do is you're going to form barium carbonate. Okay, so barium carbonate is an insoluble salt and it forms a solid. Okay, so you are going to write everything as ions except for barium carbonate, which is not going to break apart again. If it bumps together, it doesn't break apart. So barium, these are all ions. This is called the net ionic equation, or this is called the Ionic equation. And now you're looking for spectators. Anything that's on the same side. So here's nitrates on the same side. Here's sodium's on the same side. These are spectator ions. Get rid of them. What are you left with? You're left with barium and carbonate making barium carbonate. And this is called the Ionic equation. And the net ionic equation are what two ions do you put together to make something that doesn't break apart again, is insoluble, that insoluble salt. This will break your brains if you do not study it. I will try to help you all I can. I'll see you in class.